Good afternoon, everybody. My name is Corey Shambly, and I'm a senior in the Ocean Engineering program here at the University of Southern Mississippi. And I'm going to talk to you all a bit about the project that I've been working on for the past year, which is the design of a proof of concept autonomous profiling float. So before I get into the details of my project, I'm going to give a little bit of background on what exactly autonomous profiling floats are for those unfamiliar. They're a specific type of autonomous underwater vehicle that collect a variety of different ocean parameters below the surface. So the movement of these profiling floats is controlled only in the vertical direction through the use of a buoyancy engine. And if you're unfamiliar with buoyancy systems, I'll be covering that in a little more detail in a couple of slides. But they only control their vertical movement while the horizontal movement is determined by waves and currents. So you can see here's the typical mission of a profiling float. It changes its volume to sink down, it drifts for a specified period of time, descends further to begin collecting a profile, returns to the surface, and then transmits that data. So the most prominent profiling floats are deployed by the Argo program. This is an international collaborative effort. They've been going since 2000 and have nearly 4,000 floats deployed. As of today, actually, if you look at the map, you'll see that this is a map from today, May 9th, 2024. So the benefit of the Argo program and being a part of the Argo data stream is that they provide near real-time data, and they can generate maps like this and data daily. They collect data on temperature and salinity, among many other different parameters in the ocean. But this is critical for examining climate change on our oceans. And autonomous profiling floats are arguably the most powerful tool we have for examining how climate change is impacting the world's oceans. So the motivation for this project is that there are currently no profiling floats that are rated for waters under 1,000 meters. If you notice from the map on the last slide, all of these floats are located out past coastal areas. There's a lot of international research that's been going on for years into developing coastal autonomous profiling floats. And there's been a lot of advances, but still nothing that has been brought to market. And this is the result of a number of different operational hazards that result from operating in coastal environments. So you have density gradients that are created from estuaries discharging water into the oceans. This creates, you have saltwater, freshwater mixing, creating these density gradients that causes profiling floats to basically become neutrally buoyant at depth and not be able to return to the surface. You have wave activity. This is maybe the most critical and the most difficult to overcome, but along coastlines, you've got waves that are going to be interacting with the profiling floats, and there's always going to be a force that's propagating toward the shoreline that wants to push these profiling floats ashore. Hurricanes and severe storms, this kind of leads into the wave activity. When you have these severe storms, you have increased wave activity. In coastal zones, the water is a lot warmer, and warmer waters means that you have more marine life, which means biofouling becomes a huge concern in coastal zones where the depth isn't as great. And then, of course, you have ship traffic moving in and out of ports. If you have a float that's located at or near the surface, you always run the risk of some kind of collision that could potentially destroy your float. So, obviously, addressing all of these concerns and developing a coastal autonomous profiling float that operates effectively is too much to accomplish for one person. So my purpose in this project is simply to develop a proof of concept autonomous profiling float. So now I'm going to get into a little bit of the technical details surrounding my project, and beginning with the variable buoyancy system that I briefly mentioned 2 slides ago. So variable buoyancy systems are what allow these AUVs to essentially change their volume while keeping mass constant. And they do this through one of several mechanical processes. The two most prominent mechanical systems that you'll see to change the volume of profiling floats is a hydraulic system, shown here, where you have a piston or a pump transporting hydraulic fluid from inside the float to outside the float. There's an external bladder on the float. So this has the effect of, again, keeping the mass constant and raising the volume. So when you keep mass constant and you raise the volume, you essentially have the effect of lowering your density. And so the other system is a piston-style system where you have a piston that moves in and out of some kind of bearing, and water is allowed to flow into the resulting cavity that's created, and it accomplishes the same goal of essentially changing the overall volume of the float while keeping the mass constant. And you can, if you move your piston far enough, you can change it so that you go from having a positively buoyant force to a negatively buoyant force, and vice versa. So the variable buoyancy system chosen for this project relies on a simple piston system where a piston is driven along a bearing in the bottom end cap of the float. So the piston retracts, allows water to come in. This has the effect of lowering the volume, increasing the density. The float sinks. The piston can extend back to its original position to restore that positively buoyant force and return to the surface. So if you look at a free body diagram of the float while it's both descending and ascending, you'll see that you always have your gravitational force pointed downward, your buoyant force pointed upward. All that changes is your drag force, depending on which direction you're moving in. So as you're descending, your drag force is pointing up. As you're ascending, drag force is pointing down. So drag force is the opposite of the direction of motion. And so deriving an equation from this free body diagram at terminal velocity yields these equations. So basically, at terminal velocity, you have no accelerations, and you can consider it an equilibrium. So I use this knowledge to determine the stroke length of my piston by assuming a reasonable terminal velocity, which was 10 centimeters a second. So by using the formulas for the buoyant force, for the drag force, and the gravitational force at terminal velocity, under certain assumptions, such as the drag coefficient, I was able to actually determine how far the piston needs to move. And what I found is that given a 3/4 inch diameter piston, the stroke length needs to be about 0.8 inches to accomplish a required volume change to allow it to sink to approximately 8 feet depth. So getting into the design concerns of my variable buoyancy system, the primary concern, and I'm going to get into a little more detail on the specifics of my motor later, but for the purposes of talking about the variable buoyancy system now, I have to mention I chose a non-captive motor for this project, and the way a non-captive motor works is that a lead screw moves axially through the motor itself. And so if this lead screw is not restrained in some way, then it's going to rotate. And that's something that's undesirable when you have a piston that needs to be sealed against water. So I had to work around, find a way to constrain the non-captive motor. So to solve this issue, I designed the float so that it has linear rods that are attached to the end cap and then attached up here. And I designed a guide plate with linear ball bearings, essentially press fit inside them to travel along. And so this guide plate here is mounted to the top of the lead screw, and as the motor receives signals to move, It wants to rotate, but it's constrained by this guide plate. So another design concern is that as you have a piston moving alongside the inside of a bearing, there's going to be some type of friction occurring. So it becomes really important to have your bearing material something with a low friction coefficient for more efficient operation. You want to minimize that frictional force, otherwise it could become dominant and cause a lot of issues down the line. So something like Delrin. Delrin is often used in ocean engineering applications, and it has a very low friction coefficient that would allow minimal friction during movement. So now I'm going to move into the mechanical design a little bit. You may have noticed from the previous models, profiling floats are generally cylindrical in shape. You'll sometimes see them spherical, but this is for deep water applications when you see spherical floats, because sphere is just the best shape for withstanding high pressures. So for the mechanical design, I just chose simply an acrylic tube for the pressure vessel body. I mentioned that the idea for testing is to have the float operate up to 8 feet of water, which is approximately 2.5 meters. If you start to get too deep, the pressure becomes an issue and can actually crush the acrylic pretty easily, but at 8-foot depth, it's not a concern. It has the added benefit of being see-through for educational purposes, so you can see it in operation. It's good for troubleshooting as well. Top end cap, so this attaches to the top here. It's got O-ring grooves right here for sealing. And the idea is to have electronics mounted in the top end cap right here. You have a bottom end cap, which, as I mentioned, provides the bearing for the piston, but you also have mounting points for your linear motion rods, and you also have a through hole that goes straight through the end cap for mounting a pressure sensor as well. And there's a cage interface right here. This cage interface is used for both mounting the motor and housing all of the batteries that power this motor. And I also designed a locking mechanism. Essentially, there's a tab that comes out on the top end cap. It slides in to lock the cage interface into rigidly against the top end cap. This isn't an ideal design, and on future iterations I already have some ideas on how to improve this design for the locking mechanism, but as of right now it's functional. So moving into the motor selection, I mentioned that a non-captive motor was used. This is opposed to a more conventional or captive stepper motor. The non-captive motor, you have the lead screw that moves all the way through the motor. These are especially useful when you need to optimize space, because the total length of your lead screw could be shorter for moving through the motor. So you can actually save on space by having non-captive motors. So I looked into using both NEMA 14 and NEMA 17 stepper motors, and I was looking to see that they could provide enough force at a 2.5 meter water depth to essentially push the piston back to its original position, restore the volume, and allow it to return to the surface. So I did some theoretical calculations on what kind of force it would need to apply at a 2.5 meter water depth, and came to approximately 6.25 pound force that needs to be applied at that depth. So I tested both of the motors on a 35 kilogram capacity scale. So essentially what I did, it's difficult to see here, but I mounted the motor onto a table with 2 clamps, and essentially I had the lead screw move downward onto the scale and see how much of a force it could apply. For the NEMA 17 motor, it reached max capacity of 35 kilograms on the scale. So it's able to apply a linear force of, at minimum, 350 newtons, which comes out to about 76 pound force. And the NEMA 14 reached about 13 kilograms on the scale, giving approximately 28.8 pound force. Now, these are both sufficient for the depth that I want my profiling float to operate at. So for the sake of space optimization, it's with a NEMA 17, things would be even more tightly crammed. And you'll see later that it's already tightly packed with the NEMA 14. But to optimize space, I went with the smaller design since it is sufficient at these depths. And here's just kind of a look at various components used. So what I ended up doing for the top end cap, the bottom end cap, cage interface, and several other components, I used 3D printers to print these components. So here's 3 of the different 3D printers I used. That's why you have everything in different colors. But yeah, over the last few weeks, I've spent a lot of time in the lab working with the 3D printers, troubleshooting 3D printers when issues arise. And then here's a look at the assembled float in its current state. So now pivoting into the electronics, the way that the need for these electronics, what I'm going to get into now, you have a microcontroller. It reads from a pressure sensor, and then it sends a signal to the motor in response to these readings. So essentially, it's reading pressure, and it's telling the motor to either retract the piston or extend the piston. Motor driver, shown here, was used for efficient operation of a stepper motor. A voltage converter that can both step up and step down the voltage was used to control the voltage supplied to the NEMA 14 motor. So I used 4 3.7 volt lithium ion batteries and used the buck converter in this case to step down the voltage to the 9 volts, which is the NEMA 14's operating voltage. And here's just a look at some of the early prototyping I did. You can see here I was originally using a different microcontroller, but because of, you can see how tightly crammed everything is, it was going to be next to impossible to fit a microcontroller of this size in here. So it became really critical to select electronics that were as small as possible for this project. Moving on into the software code. The code was written in C++ using Platform.io, and this is how code was uploaded to the microcontroller. So the way the code was written is that the microcontroller reads measurements from the pressure sensor every second, and then the motor is driven in response to these readings. There's a library called RemoteXY that was used. The way RemoteXY works, they have a website that's free to use where you can go and set up your own app to communicate with microcontrollers that have Bluetooth capabilities. So here's a look at the app I created. The purpose of doing this is to have a toggle switch that when toggled on, I can begin the float's mission. So when the on switch is pressed, the microcontroller starts reading from the pressure sensor and driving the motor in response. And on the RemoteXY website, it'll generate all of the code for you. You can essentially copy and paste it and integrate it into your existing code to accomplish a wide variety of tasks. So now's a good time to mention that as of yet, because of the 3D printed end caps, 3D printed piston, this hasn't been tested in water. For testing in water, it's going to require the use of a PID controller. That's a proportional integral derivative controller. And this is just a kind of a feedback control system. It'll be used to control the speed that the motor operates. So I took a PID controller from a previous student and adapted it for my purposes. And it's been integrated, but for water testing, it needs to be experimentally tuned, which means putting it out in the water and testing how well it works, and then tuning it in response to those water tests. So now moving on into the skills learned and utilized. For all of the mechanical design, all of the models shown earlier, everything was completed in Autodesk Fusion, which is a computer-aided design software. I worked a lot with electronics design and programming, a lot of 3D printing, writing code in C++, and then learned a whole lot about the design of variable buoyancy systems and physics and fluid mechanics to determine dimensions and the finer details of those variable buoyancy systems. Soft skills, working on time management. Time is short during this project period, and you've got to really manage your time wisely. Communication, we get up in front of all of our classmates and professors every week, and we have kind of an interactive presentation where people can interrupt you at any time and criticize you, and you've got to be ready to respond to that criticism at the drop of a hat. And then decision making. At the end of the day, I'm the one doing this project. There are difficult decisions that have had to be made along the way, and I've had to make some of those difficult decisions and then live with the consequences if it ends up not being the right decision. Successes and areas for improvement. So these are both kind of related to assembly and fabrication. Everything went smoothly once I got started putting everything together. However, the research period carried on for far too long. So in general, fabrication should have started much earlier. And during that research period, I spent a lot of time focusing on stuff like the pressure vessel, things that are less critical at the kind of depths that I wanted to be testing at, and not focusing on the bigger picture like the variable buoyancy system. I spent a little too much time looking a little too much into different types of variable buoyancy systems when really I should have just pulled the trigger much earlier and started experimenting and fabricating stuff much earlier. And another issue I had that's kind of related to the time management, I mentioned that I had improved my time management skills, but that's really only in the last couple of weeks that I feel like I've improved my time management skills. Up until then, I had a big issue with setting deadlines and then sticking to those deadlines. So getting into the surprising aspects of this project, the design of variable buoyancy systems is complex. I thought, a month or two, I would be able to nail down some of the finer details of the variable buoyancy system design. But there's a lot of math, a lot of calculations that go into coming to these conclusions about, how far does the motor need to drive the piston. So it's a complex process, and I still haven't, figured everything out. It's going to require more research. And another surprising aspect is that the second semester really does go too quickly. The professors warn you at the very start, but you just kind of tell yourself, oh, it's going to be fine. But really, it goes by very quickly. So moving on to the results and conclusions. Obviously, this design is multifaceted, interdisciplinary. You see here it involves mechanical design, coding, working with electronics, lots of math. So yeah, it's a complex topic, and further research is going to require more funding and ideally a team of experts working with me. But at the current state, the idea I have is that the best approach is going to be to design something that's low cost and disposable. I mentioned the operational hazards at the beginning of the presentation, I don't think it's going to be feasible to overcome all of these operational hazards. And going forward, I'm looking into the design of something that's sold at a fraction of the cost of profiling floats that you'll see on the market, something that can be lost. So in its present state, the float needs end caps and piston machined, and it needs to be fitted with O-rings to provide a seal, and then it's going to be ready for water testing. So that's what I'm looking into right now. And I'm also researching the environmental impact of components. If it's going to be disposable, you need to make sure that whatever you're putting in this float is not going to be harmful to the environment. So this kind of leads into my next steps. Post-graduation, I'm going to continue my education with the University of Southern Mississippi in their MBA program. This is through the Ocean Engineering Entrepreneurship Pathway Program, and I'll be starting in fall 2024. And so during the MBA program, I'll have the opportunity to continue the development of my profiling float and attempt to commercialize the design. So the work on this project is not yet completed. It's going to continue after this. And my immediate next steps involve preparing the profiling float for water testing. So just a quick look over my budget here. When all was said and done, the total came out to just over $500. I did get some grant funding for this project and still have about $250 left. I don't have enough money to get everything I want, so I've got to make some hard decisions for my next steps in this project. But that concludes my presentation. Thanks, everybody, and I'll now take questions.
What was the most frustrating aspect of the project?
The most frustrating aspect, I would say overall the mechanical design in general. I mean, you've got everything's interconnected, and so it's easy to change one thing on your mechanical design and then have all these other issues that are created as a result. But I would also say that while that's the most frustrating, it was probably also my favorite part of the design. I like working with mechanical design. I like working with CAD software as well. So it's frustrating, but it's also a gratifying experience whenever you figure something out.
Yeah, may I twist that question to what was the most rewarding experience throughout this project?
Well, I have this here. I would just say the fact that everything more or less came together at the end. That's very rewarding. For a while there, it looked like it wasn't all going to come together, and I was freaking out in the last few weeks. So to be holding a product right here, that's rewarding for me. Yes.
So do you have a name for it yet?
No name, but I'm open to suggestions. It's going to live here at the lab, so I figure everybody has input on what the name is.
Will be known as Corey Float. The name of animal Wally HR. We got splash notes, but it doesn't go bad as green.
As Dr. Newt said, I've got component color cycling turned on my actual float.
Other suggestions. That sometimes the density curves and stuff that are out there, you might want to have like a little procedure in your float. Like if you start, get a certain depth, and then you already extend the say third of your piston.
Yeah.
It has to go all the way to increase the volume.
That's a good suggestion. Yeah.
That's something you want to think about.
I imagine so I'm kind of just taking this one step at a time. So I'm really focused on pool testing right now. And the operational hazards are going to come at some point. And so that's something to keep in mind for then. But right now I'm really focused on getting things ready for that pool testing.
Any thoughts of how long the battery will last if you come to one?
So I did some I did some calculations earlier in the semester, but if I'm remembering correctly, they were for the NEMA 17, so this was before I switched over. So off the top of my head, I cannot answer that question. I would have to go back to my notebook and run some quick calculations.
So,
Yes.
Corey, the motivation was that most, if not all, of the Argos are in deeper
Correct.
waters,
Yeah.
and you wanted to design something for shallow water applications.
Correct.
If an Argo gets trapped and surface, right?
Right.
So, in the current design, is there a design element that takes that motivation into account and makes this a uniquely different?
At this stage, not really.
Design?
At this stage, no. But the plan is to start implementing some of those
Yeah,
at a
so,
certain
so that
point.
was going to be my question. So if you think of that motivation, how would you modify this design to kind of like,
So,
other than what Marty said, the contingency?
right. So, I'm hoping that I can learn more about obstacle avoidance. Essentially, if it's colliding with some kind of object, it's able to realize that it's colliding with some object and take some sort of corrective action. So I think
I think you shouldn't hit it. If you hit anything, you will lose.
yeah, it's a good point. Yeah,
Yeah.
So it needs to
I was
have-
thinking of a scenario that nothing hits it,
right.
but for some reason, there's such a high density gradient that it cannot change the buoyancy enough.
Sure.
If I understood
So
correctly, your plan was just to build something which is cheap enough if it gets lost, because it gets lost.
yes, but the idea is to work in as many solutions as I can for these operational hazards, but not to, spend too much time focusing on them. The idea is to, most of your profiling floats are like $15,000 to $150,000. So my thinking is, if you can offer something small like this that is at a fraction of the cost, a third or even cheaper, then it might be feasible for people. But I would say it doesn't need to have. We don't need to lose 100% of them, or people, probably will not keep buying them. So there do need to be some sort of solutions implemented, but that's part of future research at this point.
There is the point, recovering them is not so easy.
Right.
If you can have a business model that is cheap enough that the recovery is actually not worth your time and money spent, then you can say one-time thing. And you get your
That's
data. That's the end of it.
Yeah, that's something to consider.
You will have to have transmission data and regular.
Yeah. So I know Iridium satellite is not a cheap thing to implement. So maybe something like LoRa, where when it's at the surface, it can find some way to transmit the data. A much cheaper alternative to Iridium.
Yeah, I think very good. Anybody else?
All right. Thanks again.